Um, we will go today over the module 4 in Principles of Chemistry 1 or General Chemistry 1. We'll go over the chemical reactions stoichiometry. So let's start. First of all, we'll learn about balancing chemical reactions. And as you see here from the figure here, this is the balancing chemical reactions. All about is the number of the atoms at the reactant sides, which is this is the reactant sides, correct, has equal the number of the atoms at the product side, which is the right side. And if you look at this carbon at the left side, the reactant sides, and of course they are separated by this arrow, separated between the reactants R, the reactants, and the products with P products. So carbon atom, 1 1, hydrogen atom, here it is, I'm looking at this. Hydrogen is 4 atoms, hydrogen is 4, you can see them here. This is hydrogens here, those are 4 of them here, 4 4, and they are there 4 4 in H2O. So then you have oxygen, 4 oxygens, those are the red ones here, and we have 4 oxygens, 2 in CO2 and 2 in H2O. So this chemical equation is balanced, and we will learn the very unique way how to balance those chemical equations. Will come soon. So the reaction above has one arrow, correct? This is one arrow, and you can see the reaction needs a little bit of heat. So at the beginning, because it has to overcome the activation energy, but then in the progress of the reaction itself does not need any heat. It does generate heat, as a matter of fact. So it is an exothermic reaction, and this one arrow means the reaction goes to completion. There's some reactions they don't go to completion, and we have a double arrow. This called chemical equilibrium. It's a chemical reaction. However, after the reaction is done, you'll get the product is present, the reactant is present, and all the reactants are present at the same time with different amounts. Here in this reaction, after the reaction is done, the reactants are consumed. There's nothing left out of methane or oxygen, just only CO2 and H2O, so complete 100%. So that's the difference between complete chemical reaction and equilibrium, which is partial chemical reaction, because we can see the products and the reactants are present at the same time. When balancing this chemical equation, we have to give really close attention between two numbers here. This number here called number of moles or coefficients, correct? And we have not to mix them with the subscript. The subscript here, those are the subscripts here, as you can see. Those are part of the molecular formula of the compound or the molecule. So we are not allowed to touch any subscripts whatsoever. We are always balancing what? The number of moles. Or coefficients. We change them here, see here, until we get everything a number of atom balance at the reactant side with the product side. But we are by all means not touching the subscript, which is part of the molecular formula and should be not really touched. So let's go further. General procedure to balance chemical equation. I intend to do, this is my own approach. I will keep the polyatomic anion as one unit. I'm not taking them apart. Keep them as one unit and then balancing them as one unit. And I look at the standalone element at the last. At the last, I look at it, not at the beginning in the chemical equation. And then balance the remaining atoms if necessary using fractional coefficients. Sometimes I have to go fractional coefficients to balance them. However, nature will not support a fractional number of atoms. There is no fractional atoms. There is no half an atom or 1/3 of atom. Therefore, I have to get rid of the fractional by multiplying both sides of the equation by the whatever the fraction number is to get rid of the fraction. Nature will tell us also that whenever I have an odd number at the reactant, for example, or the product side, and the even number of atoms at the other side, reactants or product side, it means that I have to go through fractional coefficient balancing. And always count the number of atoms of identical type both sides the equation to make sure that the amount at both sides the amounts are identical. That's what the end of the balancing chemical equation is. Check, last check that everything is good. The numbers are both sides, reactants and product sides are correct number of atoms. Let's look at this. This is a butane. This is a combustion reaction with oxygen. We get CO2 plus H2O from the combustion, plus it generates a heat, exothermic reaction. That's what I said at the beginning. But it needs heat though. It needs heat. So we have to eat heat at the beginning because it has to overcome the activation energy. So as soon as the reaction had overcome the activation energy, it starts generating by itself heat. So it's an exothermic reaction. Let's look at this equation. Let's balance it. It's very interesting because we will see we have a fractional coefficient balancing here. So let's put a table, and this is my approach. As I said, this is my own approach. I like the table. So I can keep track on everything in a table here. So I go for the reactant sides, okay, and here's the product side. I'm not balancing the heat. The heat is out of our touch. Keep it as is. I say in the number, the table will be number of atoms or polyatomic ions. So we have carbon, we have hydrogen, we have oxygen, 3 atoms. Do we have polyatomic anion? No, we don't have. So this is the reactant side. That's left, that's the reactant side. And this is the product side. Now, if you look at this, I'm looking at the number of atoms at the reactant side. I have 4, here it is. I have 4 carbon, 10 hydrogen, and 2 oxygens. And in the product side, I have 1 carbon, I have 3 oxygens, I have 2 hydrogens. All those not balanced. So my intuition will tell me I have to multiply the carbon here, the carbon dioxide, by 4. And I have why to balance the carbon. And I have to multiply this H2O by 5 to get the 10 hydrogen, to balance the hydrogen. So that's what I'm doing here. Look at this. The hydrogen multiplied by 5 to get the 10 to the equal to the left side. And the carbon has to be multiplied by 4, that's in the right side, to get the 4 at the number equal to the 4 at the left side. Now, see here, nicely I put 4 and 5, correct? Now, carbon, this is 4 and 4, the carbon is balanced. The hydrogen is 10 at the reactant side, 10 at the product side, it's balanced. Now we have a problem here, it's not balanced, it's the oxygen. Why? The oxygen in the left side is 2. And in the right side, 4 multiplied by 2, this is 8. And 5 multiplied by, this is 1, understood, not written. And this is 5. You add them up, correct? Will be 13. Here it is, 13. So now I have, this is, and the reactant side is 2, that's even number. And the product side is odd, 13. So this will tell me in my intuition, I have to go through fraction. I have to go through fraction because they are not even, they are not odd, they are different. So odd and even, I have to go fraction. So I'm going through fraction now. I have 13 at the right side, so I put the fraction here, 13 over 2. And this is balanced now. This is a balanced equation. But nature tells you, no, no, no. There is no 13 over half of an atom oxygen. There is none. So I have to get rid of this fraction out of the, what? Out of the equation. So I multiply the underneath here. I have to multiply it. Multiply the denominator, which is 2. Multiply the whole equation by 2. So this, the whole equation by 2 will be 2 butane, 13 13 oxygen, 8 CO2, carbon dioxide, and 10 H2O. Of course, plus heat. Of course, plus the heat itself. Okay, so now you can verify it. You have 2, 4, you have 8 carbon, and here you have 8 carbon. That's correct. Carbon is okay. You have 20, 10 multiplied by 2, 20 hydrogen. You have 10 multiplied by 2, 20 hydrogen. Hydrogen is balanced. You have 13 plus 13 multiplied by 2, 26 oxygen. You have here 16, 1, 6, correct? And here you have 10. So this is 26, and oxygen is balanced. This is the correct balancing of this chemical equation. Now look at another feature of balancing chemical equation. If we are dealing with aqueous solutions, we have to state the status of, or the state of the matter itself. So we have to add S for the solid, G for the gas, and AQ for aqueous, and L for liquid. Those has to be subscript or added after the molecule or the compound to specify the state or the states of the matter of the molecule or the compound, correct? So now, if I look at the chemical equation we did, butane is a gas, oxygen is a gas, carbon dioxide is a gas, H2O is H2O is a gas, steam, and the heat is there too, and this is an exothermic reaction because the heat is given away. Another reaction here, and as I said, the first reaction, this reaction is called combustion. Just to recall, this is combustion. We'll come back to this. The second reaction is decomposition reaction. Mercury 2 carbonate heated will give us mercury 2 oxide and CO2 gas. This is another exothermic. Ammonium chloride, correct, gas, heated, absorbing the heat, you get ammonia decomposed, and HCl. That's an endothermic reaction. So the heat has to be put in, correct? The heat has to be put in for this reaction to decompose ammonium chloride. If you look at this, the mercury 2 oxide solid, mercury 2 oxide, mercury carbonate 2 carbonate is solid, mercury 2 oxide is solid, CO2 is gas. So we are stating the whole thing. Ammonium chloride gas, give you ammonia gas, HCl gas. And we give the heat if it's exothermic or endothermic. Now we'll go for balancing chemical ionic compounds in aqueous solution. Aqueous means dissolved in H2O, and our water is the solvent. The solvent is water. So we have 3 types of aqueous solution that can be balanced in aqueous solution. And the first one called complete molecular ionic chemical equation. The second called complete ionic chemical equation. And the third one called net ionic chemical equation. As you can see, all those ionic compounds, all those are ionic compounds, correct? The difference is this: molecular means that's the whole compound in a molecular type of structure. We don't take it apart as a whole molecule. Complete ionic, we take this chemical compound, ionic chemical compound, into ions, take it apart into ions. The net ionic, then you will see, this is ionic compound, but we have gotten rid of all the ions that are not participating in the reaction. The chemical reaction, we just kept the ones that are really responsible for the chemical reaction, as you will see now. Now let's look at this. I have, this is a chemical reaction called complete molecular ionic chemical equation. Why is complete? Those are ionic. All those are ionic compounds, correct? Those are ionic compounds, and what we can say about these ionic compounds, those are not separated, those just in a molecular type of writing of a molecule. So therefore the molecular means they are in one unit, so they are not taken apart yet. And then we have aqueous, correct? Aqueous, the lead 2 iodide is solid. This is the only one solid here. This is the only solid. And sodium nitrate is an aqueous, correct? Now, we don't take any ions as a part. This is molecular ionic, complete molecular ionic compounds. Now we have to balance it first. We have to balance it before. We cannot go further without balancing it. So we not touch anything the subscript. We are touching just the coefficient. So now looking at this, correct? Looking at this here, I have 2 nitrate as polyatomic, and here I have 1. So my tuition will tell me I have to add here what? 2, correct? So I have to add here. So I have to add balance here. I have to add 2 here, which is here it is, correct? I have then 2 nitrate and 2 sodium. And I have to add here 2 to balance it. So now the whole thing is balanced. The only solid is this. All the other ones are aqueous. So the next is complete ionic, not molecular, but ionic. So take the molecular word out. So this is the key here. This is 1 unit. Now we are taking the complete ionic. We are taking all those compounds into their corresponding ions, correct? So this is 2 sodium aqueous. We'll take apart all the AQ only. The solid, this will be intact. It's not touched. The liquid is not touched. The gas is not touched. So solid, liquid, and gases compound are not touched. Keep them as they are. As what? As they are. Don't touch them. Don't take them apart. So only the aqueous. So now 2 here, AQ, take it apart. It's 2 here, means 2 sodium ion plus 2 iodide ion. Lead 2 nitrate, lead 2 aqueous, and nitrate is 2 of this. The 2 here will come in front. Nitrate is a polyatomic ion, aqueous. This one is kept as is, not touched. Then I have sodium is 2, nitrate is 2. Those are ions, correct? This is called complete ionic chemical equation. So I took all the ions, all the chemical compounds, and take them apart into their corresponding ions, leaving the solid here untouched. If I have a liquid, I will leave it untouched. If I have a gas, I will leave it untouched. So further, now we'll come to the net ionic chemical equation. The net ionic, we have to get rid of the ions that appears in the product side as well, in the reactant side as well in the product side. So we have ions are appearing in both sides, such as sodium here appear here and sodium appear here. So I can take the sodium here. I can take the sodium out. Nitrate, in the second thing here, I can take nitrate out. I can take the nitrate out. Discard them, okay, to get the net ionic chemical equation. Now, as you can see here, that's what I did here. So those are out. Those are called spectator ions. What means spectator ions? They are chemically inactive. They are chemically not involved in the real chemical reaction. The chemical reaction is whatever left. Those are producing something, correct? Producing a product. So this is then the net ionic chemical equation is 2 iodide anion plus cation lead 2 give you lead to iodide, solid, aqueous, and this is the net chemical equation. And as a matter of fact, the net ionic chemical equation is really the very important chemical equation, ionic chemical equation. Why? Because it shows us what are the species of the ions are really taking part in the chemical reaction. So all the sodium and nitrate in both sides, they are there inside the reaction, but they are inactive, chemically inactive. So we call them spectator ions, watcher. They watch the chemical reaction without participating in it. Okay. This is another example here. I replaced the sodium with potassium. So I have to first balance the chemical equation. Correct. I have to add 2 and 2. Here have a 2 and 2, correct. And the complete ionic chemical equation will be take apart that's the molecular one. This is the molecular one, the top one here. This is the molecular one. With balancing, here will be 2 and here will be 2. So, and then the complete ionic chemical equation. So take everything apart except the solid, liquid, or gases. Keep them untouched. So we are keeping this one untouched because it has solid. All the AQ will be taken apart. AQ taken apart. Now the net ionic chemical equation, the spectator ions, they are appearing in both sides. Here nitrate out, potassium ion and potassium ion is out. So the real reaction, the real driving force of the chemical reaction, of ionic chemical reaction is, this is between iodide and lead 2. So this is the net chemical equation, and this is the driving force for the chemical ionic reaction. So now let's look at the chemical reaction types. There are three major reactions, some of which have subtype of chemical reaction, as you will see later on. All these types of reactions, chemical reaction, considered to be in an aqueous medium where H2O is a solvent. Those are participation reaction. There is another name for precipitation. Precipitation reaction is well known as a double replacement or displacement. So precipitation make a solid, precipitate. Precipitate means make a solid that's not soluble in H2O, in the solvent. Acid-base reaction is also known as a double replacement or displacement. So those are another name for them, double replacement or displacement. Also, acid-base reaction is called double displacement or replacement. There is a third name for it called neutralization reaction. Neutralization, acid-base neutralization reaction. Redox reaction. Redox reaction, it has several reactions. Redox reactions, as you will see the definition of redox. Red means reduction, and ox means oxidation. So reduction oxidation reactions can be involving single replacement, decomposition reaction, combustion reaction, or reactions, and combination or synthesis reaction. All those four, they will go underneath the redox reaction. Let's look at the precipitation reaction. Precipitation reaction, as I mentioned, it has to produce a precipitate. Precipitate is a solid formed during the ionic interaction. There is intermolecular ionic forces between the anion and the cation, leading to attachment of the cation to the anion to make a solid, which is not soluble in H2O. Here is an example here, very nice red precipitate of silver nitrate with the potassium dichromate will give us silver dichromate. So this is the color here, very nice. This is silver dichromate, which is really very nice red, ruby red color, very nice color. It's not soluble in H2O. This is a precipitation. You make you make a precipitation, and you can dry it. You can drive all the aqueous solution out, evaporate it, and you can get a very nice red crystals out of it. So now we look at some tables. Again, you can't memorize all of it, but at least you get the idea. There is always there is a scheme inside this solubility tables. Group number one of the scheme you have to look at this, or the chart, all alkali metal or group 1A most of the time will be soluble. So they are soluble. There's no exception. Ammonium ion, always soluble. No exception. Nitrate, acetate, chlorate, perchlorate, soluble. No exception. Now when we get into the halogens, the chloride, the bromide, the iodide, those three here, those are soluble, except, what the exception? The fluoride, it's not there, it's not soluble within the halogens. Then we have those 4 ions are not soluble. If I have lead, lead 2 or silver or mercury 2 combined with those 3 halogens will be insoluble. So those are the exception. And the fluoride again is not soluble, so it's not part of them there. Now all the sulfates are soluble, so all the sulfates are soluble, except, what's the exception? Those are the exception here. So those are the exception. Barium, strontium, calcium, and lead and mercury, silver and mercury too. So all those are not with them combining with sulfate, they will form a salt that's not soluble. Let's go further and look at the table. Slightly soluble ions in aqueous solution. Well, it turns out to be whatever we said before, correct? The exception, if you look at the exception here, that's the exception of the sulfate. It will come back to it showing up in the table. So here it is, the sulfate of lead, silver, and mercury. All the sulfate combining with those ions will make slightly soluble, correct? And the hydroxide with calcium, strontium will make soluble, except what? Except barium. Barium hydroxide is not soluble. And there, lead sulfate is poorly soluble. So now let's go and look at insoluble one. Insolubles are what? Sulfide, hydroxide, and carbonate, oxalate, chromate, and phosphate. All those are not soluble. And there are many other not soluble as well. But those are the very famous ones, are not soluble ions or polyatomic ions. But there is exception. Group 1A, which is coming sodium, potassium, cesium, francium, they are always soluble, correct? So group A, 1A are always with ammonium, always soluble with the sulfide. Also, potassium group 2A are with the sulfide are soluble, correct? The hydroxide, the same thing. Group 1A, correct? 1A and ammonium and aluminum are soluble with the hydroxide. The alkali metals, transition and aluminum, they are, so the 1A, group 1A is soluble, and aluminum and ammonium. All the other hydroxide are not soluble. And here's the same thing. You see group 1A is always with ammonium are soluble, correct? And lithium, a little bit, phosphate, soluble. Now let's look at this solubility rule. You balance the molecular ionic chemical equation, correct? And you get the complete ionic and the net. That's the whole key. You get the net ionic, and you get the precipitate. Take the precipitate and look at the table. Match this precipitate solubility with the table solubility. If the table says no, this is slightly soluble or insoluble or highly soluble, then you can if this is a precipitate, will be insoluble, of course. So with the help of the net ionic chemical equation, that's the key, and the table. So you can tell the table we just went through. Here it is. You can determine the solubility of the compound or molecule produced. Here is a very nice table. It's very comprehensive. So here we put in this side here, the anions, all the anions here, correct? And here we put the cation, group 1A, all those here, group 1A, those three here, group 1A. Here, correct, group 2A, group 2A. And as it said, magnesium, calcium, barium, and lithium, sodium, potassium. That's an example of group A. And here the transition elements. Here are transition what? Elements. So there are transition elements. And here other elements such as lead and aluminum. So here is lead and aluminum. So now, if you look, they are color coded. So the green is insoluble. This color here, the light purple here, is slightly insoluble. The white ones here is inapplicable. Leave them blank. And I think, yeah, soluble slightly, and the rest is soluble. So the blue one here, the larger, is soluble. You can see the majority of the ions are soluble. See all of the blue or light blue, they are soluble. Very few greens, you can see very few greens, they are not soluble. And the light purple here, they are slightly soluble. Okay, and you are matching this way. Look at this. I have here, for example, both I have aluminum 3, match it with, here it is, fluorine. Aluminum fluoride is slightly soluble. Lead fluoride is insoluble. See here, I go by matching one element with the other, one element with the other. Here's chlorine. Chlorine with aluminum is soluble. So let's take here sulfate. Sulfate with, say, calcium. Sulfate with calcium. This is sulfate here, and the calcium is here, correct? No, that's copper. Sorry, that's copper. So solubility in not applicable. So let's take the sulfate with calcium. Here it is. This sulfate from this goes all the way to calcium here, correct? Is said insoluble, and that's really true, insoluble. So you match these anions with the cations at the top, and look at the whole thing. And as you can see, majority of the ions are soluble, and very few are slightly insoluble, and the fewest is the slightly soluble. So that's what it says from this comprehensive table. Acid-base titration. So acid-base titration called acid-base neutralization, correct? Or sometimes called double displacement or replacement. So an acid will come and, correct, here it is, will react with the base. This is an acid, hydrochloric acid, react with sodium hydroxide to produce a salt, sodium chloride, and H2O. And we have to have this status of the matter here, of the compound or the molecule. HCl is aqueous, sodium hydroxide is aqueous, sodium chloride is aqueous, H2O is liquid plus heat. It's an exothermic reaction. So we have all the details about the complete molecular. This is molecular. We are not taking anything in apart. So this molecular ionic compound, correct? Now, if I look at the whole thing and I want to really to take it to the correct, to complete ionic, so I have to take everything aqueous except H2O. This is liquid. I cannot touch it. H2O is liquid. I can't touch the solid, the liquid, the gas, correct? So I'll take this HCl, H, plus Cl, those ions. Then sodium hydroxide, sodium and OH hydroxide, all of them aqueous. And the product sodium chloride, sodium and chloride aqueous. The H2O will remain as is, no touching. Correct? Now I need the net ionic chemical equation. Well, yes, I can. Sodium here appears the other side, sodium. So here it is. So I can take it out. So the chloride, another one, I can take it out. And the chloride, I can take it out. So what's remaining is, this is really the net ionic chemical equation. So with the heat is there, it's exothermic reaction. So what it says that the titration or the neutralization between acid and base has a driving force is producing H2O. So it said, and this is very, very important to know, that's an aqueous solution. This is all about aqueous solution. So if you have a non-aqueous solution, that's different story. So the driving force for acid-base reaction or neutralization in aqueous solution is always forming H2O, correct? From the reaction of the protons with the, which is really protonium ion, with the hydroxide ion. This is the driving force of the acid-base neutralization reaction. There are two types of acids according to their dissociation in H2O. We have strong acid and we have weak acid. Strong acid is an acid that dissociates what? Completely. Weak acid is an acid that dissociates in H2O partially. Not 100%, but less than 100%. And you can memorize this. It's very important. We have 7 strong acid in chemistry. All the other acids, such as those, are weak. So the strong acids are perchloric acid, chloric acid, hydrochloric acid, hydroiodic acid, hydrobromic acid, nitric acid, and sulfuric acid. 7. And all the rest of inorganic, organic acid, whatever acid you can see in nature or in any textbook, it has to be, is not one of the 7, it has to be weak acid. So it does not dissociate in H2O to completion 100%, so less than 100%. So those are weak acids like acetic acid. Here they are: acetic acid, hydrofluoric acid, phosphoric acid, oxalic acid, carbonic acid, and so on. All those are weak acids. The same thing here, we can see that these weak acids are more abundant. So the strong acid, we have only 7. And the weak acids, I don't know, maybe around thousands and thousands of them are present in the vegetables and the fruits. So fruits and the vegetables, they provide a lot of weak acids, and those are all the all the veggies and all the veggies and fruits are, you can find the acids in them. So now we'll go to the bases. Well, we have the same thing. We have strong bases and weak bases. Strong bases here dissociate completely in H2O. Weak bases dissociate partially in H2O. Now again, it's the same thing. The strong always limited amount, but the weak, you can imagine every weak base found in nature, mostly in vegetables and fruit as well. So you can see the strong bases are coming from group 1A and 2A, such as sodium hydroxide, lithium hydroxide, potassium hydroxide, cesium hydroxide, magnesium hydroxide. This is group 1. This is group 1A. 1A here, correct? So here it is. And this group here, this group here, 2A. So the magnesium hydroxide, calcium hydroxide, strontium hydroxide, barium hydroxide, those are the only strong we know, group 1A and 2A. All other bases found in nature, except of those, are considered to be weak. They don't dissociate 100%. They are partially, they are dissociating to certain limit. So, and all other inorganic and organic bases are considered weak. Here, example of the weak: ammonium hydroxide, iron 3 hydroxide, titanium 2 hydroxide, aluminum hydroxide, pyridine, that's an organic weak base, aniline, weak base as well. All the amines are considered to be weak bases. And here some of the fruits, you know, are rich in weak bases: dried chestnuts and Bing cherries. So those are, they have a lot of fruits, they have weak bases. So here is an example of the acid-base neutralization, which is give us what, H2O and the salt in H2O. Now this is reaction here. The salt in H2O, this is a salt and H2O. This is if we have water is our what, our byproduct. So we have a byproduct of H2O. So if I have iron 3 hydroxide plus nitric acid, will give me iron 3 nitrate. That's a salt. That's my salt here. This is my salt here. That's my salt here. Plus H2O, that's my byproduct here, H2O. And this considers as double replacement or displacement or neutralization reaction. Now here, if you have, for example, aniline, correct? You let it, that's a weak base. With HCl, you get what? You get anilinium chloride. This is, there is no H2O. So H2O is not there, correct? There's no byproduct H2O. There's no H2O, correct? And this considered not double displacement. This considered as to be what? Combination reaction or synthesis, correct? This is a synthesis reaction or combination reaction, because you add HCl into aniline to get ionic compound anilinium chloride. No H2O as a byproduct. Now we'll get into new type of reaction. We covered the titration, I mean the acid-base reaction. Let's go and cover the redox reaction. The redox reaction, and we said redox is coming from red and ox. So we have two words: red, reduction, and ox is oxidation. We'll mention what's the meaning of both. So the sub reactions of those redox reactions can be single replacement or displacement, decomposition reaction, combustion reaction, combination, synthesis reaction. All those types can be considered depending on the reaction. Can be considered redox reaction. So redox means red, reduction, and ox means oxidation. What we mean by redox reaction? As you can see, redox means you are reducing the oxidation number. Oxidation number is the charge that carried by the ion during the reaction. If you reduce the charge of the ion, you talk about reduction. How you can reduce it? You have to, this ion has to gain valence electron from adjacent atom, correct? So reduction means you gain valence electrons, and therefore the oxidation number, which is the charge carried out by the ion, will be reduced. The oxidation, the opposite, the oxidation is losing, not gaining, losing those valence electrons, correct? and the charge on the oxidation number, or the charge that the ion carries, will be increased, not decreased. So oxidation means increase of the oxidation number, the charge, the ion that carries within the reaction, and the reduction means decreasing the oxidation number, the charge that the ion carries during the reaction. Correct? And here's the definition of oxidation number. Is the number of the charge that an atom or molecule compounds can carry when they are found in the solution or as ions, correct? During the chemical reaction. Here we have, if you look, just general rule, so you don't have to memorize it, but you'll get the idea into it as you see a lot of example. So you make some worksheets, you watch some videos. So the oxidation number rules. All neutral atoms or molecules or compound, correct? So here it is, have oxidation number of 0. Example, if I have iron, phosphorus, sodium by themselves atom, they're sitting in the chemical reaction like this, they have oxidation number 0, correct? Also, all molecules, such as oxygen here, sitting in the chemical reaction like this, nitrogen, chlorine, sodium chloride, those have oxidation number, the sum of the oxidation number is 0. Sodium carbonate, the total sum of the oxidation numbers of this molecule or compound is 0, because there's no charge on it, correct? So the oxidation number of ions is equal the charge that this ions carry. That's what I say. Oxidation number equal the number of the charge that carry. For example, calcium 2 plus, correct, ion, so it will have +2. The oxidation number is +2. Aluminum is 3 plus ion, the oxidation number is +3. Phosphorus is B3 minus, so the oxidation number is -3. So here it is. So, and sulfide is S2 minus, so the oxidation number -2. Ammonium has oxidation number of +1 because it has 1 plus positive. So, and the third rule is hydrogen always, when it's connected to make covalent bond, it has +1, correct? When it's making what? Covalent bond. But hydrogen, like in ammonia, nitric acid, and C2H6, all covalent will be +1. But the oxidation of hydrogen, oxidation number of hydrogen, will be -1 if it's connected to metal, like ionic compound, such as potassium hydride, look at this, barium hydride, aluminum hydride, lithium aluminum hydride. All these, by these, is the hydrogen has oxidation number -1. But if it is like here, ethane is +1. When hydrogen is making covalent bond is +1. When it's making ionic bond, then is -1. The metal of group 1A will have always +1, correct? The metals in group 2A will have +2, correct? Generally, oxygen is -2, unless there is some specific compound. The oxygen in hydrogen peroxide is -1, can be, correct? Ozone and oxygen. So it depends what the oxygen, but in general, I would say 99% of the cases, oxygen is -2. Group number 7, the halogens, they have -1, correct? They have what? Oxidation number -1. So here we talked about the oxidation. Oxidation is losing electrons and increasing what? Thus we talked about this. Oxidation is losing valence electrons of an atom, becoming an ion. By losing those valence electrons, the oxidation number will increase, correct? And here is an example. Iron, start with iron, 0 by itself, loses 3 valence electrons. So when it loses 3 valence electrons, iron will have what? 3 positive. So now compare this 0 here with 3 plus. The 3 plus is greater than 0. So this is an oxidation increase in the charge of the oxidation, increase in the charge, increase of the oxidation number, 3 plus. From 0 to 3 plus, that's oxidation. So the redox reaction is the redox reaction in general made of 2 halves. This is very important because it's reduction and oxidation. So the first half reaction is the oxidation reaction, and the second half is the reduction reaction. Both halves are interconnected, and they are occurring at the same time. Let's look at the example here. Sodium react with chlorine. Sodium atom react with chlorine atom. Sodium will be oxidized. Look, it goes from 0 to +1 and give away, losing its electrons. Correct? Give away electrons. This is an oxidation first half reaction. This is oxidation reaction. The chlorine take this electron here in and will be reduced from 0 -1. -1 is less than 0, and this is second half reaction, reduction reaction. So then the complete redox reaction will be the sum of both 2 halves of the chemical reaction equations, and here it is the complete redox reaction. Here's we'll go through the oxidizing and reducing agent. On this type of oxidizing and reducing agent topic, ask yourself, we have potassium 0 oxidation number, bromine is 0, and it gives us potassium plus and bromine negative. Now ask yourself, I want to see which one is oxidizing agent and which one is reducing agent. Ask yourself, what does potassium do on bromine? Well, it looks like potassium is forcing bromine from 0 to -1. This is a reduction, reducing its oxidation number, correct? So potassium is said to be what? To be reducing agent. Potassium is reducing agent, providing this valence electron, correct? So now ask another question for yourself. This is the first question here. Ask yourself, what does the bromine do on potassium? Well, bromine is forcing potassium from 0 to +1. So forcing it to increase its oxidation number. So that's an oxidizing agent. So forcing, because potassium is being oxidized, correct? So bromine is removing valence electrons from potassium. So bromine is an oxidizing agent. Let's look at one of the examples here. Sodium, we know that's plus group 1A is always +1. Oxygen 99% of the time maybe -2. 1% maybe. 99% is -2. Oxidation number 1 or 2% is maybe different from -2. But most of the time oxygen is -2, except for some compounds is -1 or -1 in some compounds, but that's oxygen. Now we have to calculate what chromium be. If sodium is +1, that's 2 sodiums, 2 pluses, and oxygen is -4, -8, so chromium will be what? +6 to make -8, because all the molecule here considered to be what? Have the sum of oxidation number of 0, correct? Oxidation number of 0. So with this way we can determine the oxidation number of the element we don't know. But we know that potassium, group 1A, +1. Oxygen always, we said, or most of the time, 99% of the time, -2. Correct? So this is 2 potassium, 2 positive, 7 multiplied by 2, 14. 14, and then you have 2, 12, -2, 12, 12 divided by 2 chromium is +6. CO2, carbon is, and oxygen. Oxygen is take priority -2, as you said. So -2 multiply 2 oxygen -4. The carbon will be +4. Methane is covalent, then hydrogen has to be positive, as we said, and carbon will be -4. Perchloric acid, hydrogen is making covalent, so it has to be +1 hydrogen. Nitrogen is -2, so the chlorine will be, you can calculate then, chlorine has to be +7. The same thing here. We have manganese, manganese 4 oxide. Manganese oxygen is 2, correct? And the manganese, so -2 -2 4, oxygen is -4, the manganese will be +4. The the sulfite, the whole charge is -2, and you calculate oxygen is always -2. So the whole thing is -2. Then you can calculate S. We don't know the sulfur, but you have 6 multiplied by -2, 6 negative of oxygen. You calculate it, and the sulfur will come +4. Fluorine is always, group 7 is always -1. -1 multiplied by 4, -4, so sulfur will be +4. So now you ask yourself, what is the range of the oxidation states of carbon? We have to go up of carbon. So the oxidation state of carbon is we saw carbon here, +4, correct, CO2, and we saw the oxidation number of carbon is -4, so +4 -4. So that's, which compound has carbon in +4? You go down, you go up here. +4 is CO2. CO2 is +4, and -4 is methane. So come here, +2 is CO2, and -4 is methane. That's good. So now let's look at the chemical reaction, the oxidation during the oxidation reduction oxidation reaction, the atoms changing its oxidation number. Let's look at this one here. We have nitrogen will react with hydrogen to produce ammonia, correct? Ammonia. So nitrogen reacts with hydrogen to produce ammonia, or nitrogen trihydride. So now let's look at nitrogen. Nitrogen by itself here, correct? Nitrogen in nitrogen here is 0, because this is very important. So but nitrogen in NH3 will be -3. Why is -3? Because hydrogen is in covalent, making covalent bond with nitrogen, so hydrogen will be +1. So 3 pluses of hydrogen will have to encountered by -3 of nitrogen. So the molecule is, the whole molecule is 0 oxidation number, neutral, correct? So, and here is hydrogen by itself here, look at this, by itself is 0, but here in the molecule is always, we say, +1. So now you can tell me which one will be oxidized, which one be reduced. It looks to me that this nitrogen came from 0 to -3. Thus, this is what? A reduction. So this is a reduction. For hydrogen from 0 to +1, this is an oxidation. Correct? So now ask yourself, let's do it question. So we know which one is oxidized, which one is being reduced. The nitrogen is reduced, correct, by taking extra valence electrons, and hydrogen being oxidized by giving away its valence electrons, correct? Now the question is, so here it is, oxidation number increases. So which reactant undergoes increase in oxidation? Hydrogen. Which number undergoes decrease in oxidation number? Is nitrogen. But the question is here, which one is an oxidizing agent? Which one is a reducing agent? Well, it turns out to be, ask yourself this question, what does nitrogen do on hydrogen? What does nitrogen do on hydrogen? Well, it turns out nitrogen is forcing hydrogen to be oxidized from 0 to +1. So nitrogen is an oxidizing agent. What does, now, second question, what does hydrogen do on nitrogen now? On this, hydrogen is forcing nitrogen to be reduced. So hydrogen is a reducing agent. So hydrogen is a reducing agent. And that's what we have here. Hydrogen is a reducing agent, and the oxidizing agent is nitrogen. Thank you very much for your attention, and we'll come